So for the IR spectra, we know that in our reactants, which is CH4 and O2, and to this combustion reaction, we'll get our products, which is carbon dioxide and water. In a complete combustion reaction, a hydrocarbon reacts with oxygen to form carbon dioxide and water. Since methane is a hydrocarbon containing carbon and hydrogen, when it burns in oxygen, the carbon atoms form carbon dioxide and the hydrogen atoms form water. From this, we can write the balance equation of CH4, 2O2, CO2, and 2H2O. The stoichiometry shows us that one methane molecule reacts with two oxygen molecules to produce one carbon dioxide molecule and two water molecules. Before combustion, the mixture only contains methane and oxygen. The IR spectrum mainly shows methane because oxygen is not IR active. After complete combustion, the reactants are consumed and the spectrum is dominated by the products carbon dioxide and water. Because two water molecules are produced for every carbon dioxide molecule, the water signal would appear relatively strong in the final spectrum.
In the XPS spectrum for copper and carbon, there's a peak for carbon, which is C1s, since there was an incomplete combustion. An example of this is when there is a fire, but the fuel does not burn entirely, and these leftovers are the carbon. This peak occurred around 284.8 eV. There is a peak for oxygen, O1s, because Earth's air contains oxygen, which most likely reacted with copper around 532 eV. This means that there was an interaction between oxygen from the air and the copper compounds. There are peaks for copper, Cu2p as well. The Cu2p 3 out of 2 peak occurs around 933 eV, and the Cu2p 1/2 peak occurs around 952 eV. The reason behind these peaks is that the copper turns into copper oxide when it gets hot in the air. Cu2p 1/2 has a peak higher than that of 3 out of 2 because of the spin-orbit coupling, which is when the electron spin causes a magnetic field when interacting with the orbit around the nucleus's magnetic field.
The mass spectrometry for molecules. Therefore, the market base, we use energy to sketch the mass spectrum of fuels for either the nitrogen bucket or the gas market base, we use fuel. So approximately we the fuel that use the rocket one, then we get a chemical sample from the solid fuels of carbon sugar alkanes and hydrocarbon compounds and aromatics and olefins. The concentration can be equal to the molecular weight, which helps us with statistical positive abundance and the mass spectrum ratio. So the formula is given as carbon to N H2 1 3 N but in order to define the mass spectrum sketch, I'll use the general formula, which is the the mass concentration breaks down as follows: is saturated hydrocarbons. Saturated hydrocarbons have a single bond between C's and the end in A and E. So for example, propane, methane, ethane, alkanes, sulfides, and carbon atoms are generally liquid and use the fuel solvents, which matches up with our description for the it also has technical aromatics olefins. So aromatics are class of unsaturated hydrocarbons. They are bonded among two C's and then E, indicating the one. So example, propane, methane. Although aromatics are unsaturated carbons, like benzene, they are not considered alkanes because they're highly reactive, which whereas aromatics are not alkaline reactions. So statistic meaning that there must be three high carbons and they're liquids and they produce a yellow sweet flame in burn. So they're used to increase density, and when increased density, the energy capacity is increased. So aromatics improve the volumetric energy density of fuel, meaning more energy can be packed into a smaller volume. So they also use for combustion efficiency, and rockets engines aromatics are required because they have flame speed and stability for combustion. Olefins are also saturated carbons, they increase density and they increase efficiency and they more refined. So in order to make the spectrum, we have to have broken down our smaller fragments. So from our initial equation here, we use the molecular weight. So carbons AMU is 12 and we also have over here, so it's 12 and 12, and then for hydrogen AMU is 1 and then calcium is 26. So when you add them together, you get 1 mass ratio. In order to see how many fragments that actually put to have a peak in my spectrum, I can see which bonds I'm missing have a factor. So carbon one is 4 bonds and we have over here, and hydrogen is 1 bond. We have here, we put this by 2, so I actually have a factor 2. So then if we space out it, 2 6 and 6 13. So my first fragment that I can do is carbon 6 and hydrogen 13. Then you just do the molecular weight, so you get the mass ratio, which is 5. And then normally when you're doing fragments, you're going to see that you take a sample, for example, like benzene, and you put it into the mass spectrometer. Sample becomes liquid ionized, and using electron beam, ionizing the atoms that have neutral electrons, transforming the neutral particles into electrically charged particles, ions, and ions can fragment radicals into ions. However, only ions, positively charged, will get the ionized energy better. So we split up this carbon and hydrogen, you get only one radical and the rest. So the one radical will go carbon forward and the rest will be hydrogen. So you'll see that this is increasing by 2 and this is increasing by 2, and this is a radical and this is the rest. You'll see right here, there's a description. So this is the one of the fragments, so this is the basic fragment, this is the common fragment, the chain cleavage, large fragment, and then you can just see other multiple here. This is my mass spectrum, so you can see that they go by kind of the molecular weight. So you have 57, 71, 85, 99, and this is the same for the carbon 9, hydrogen 19 for 1 right here. It's the same. The reason why I have the M plus right here for 170 is because we have it's a peak, it's a peak, the parent peak, and so mass component is 170, which is right here, which is for the equation for the kerosene rocket fuel gas base rocket. They use liquid methane, so the consumer compounds methane and propane. The liquid methane is for efficiency and efficiency isn't produced as much as and for rockets like use hydrogen, it's usually hydrogen methane. So you'll see a lot of things being used in the composition. So here's my use the same breakdown to make the natural gas spectrum. So here my axis is all labeled, positive abundance and charge ratio, and then to break it down, here's the molecular weight again. So here for the equation is CH4. So carbon's molecular weight is 12, 1 carbon plus 1 hydrogen, 1 hydrogen molecular weight, and 4 hydrogen. So you have 16 mass ratio. So then here fragments, this will be easy. You can just go CH4, CH2, 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 You can see molecular ions, the basic right here, fragment, small fragment, and carbon. Then you just show here. Here the fuels. So for natural gas molecule size, there are small molecules, and mass ratio is 10 to 45, versus the kerosene base rocket fuel is large carbons from 2 to 170 mass ratio, and then there are many fragments are listed here, and the structures have way fewer peaks compared to the kerosene base, which has more peaks because it's in the alkane series. You can see that here.
The instrumentation used for the analytical techniques above is an IR spectrometer, an X-ray photoelectron spectrometer, and a mass spectrometer. The infrared just uses an IR source that emits light, and then it goes to a reference in a sample that gets collected into the splitter and then into the detector, which measures the intensity of the radiation. The X-ray photoelectron spectrometer starts with a beam of X-rays that bounces off a sample, and then the analyzer collects the electrons and the detector counts the electrons, and then the data is projected into a graph. The mass spectrometer works as a beam of rays going, and then the magnets on either side bend the ray into different angles, which get projected onto the detector that measures and identifies the high density spots getting hit by electrons. Comparing methane-based and kerosene-based rocket fuels, the methane is better for the environment and it's higher efficiency. However, since it's newer, there's not much information about it. Whereas kerosene produces more soot, which is bad for the environment, but it packs more energy and has been used forever. So there's more information about it and more experience with it. And so the bottom line is methane would be used for cleaner engines, for better reusability, higher efficiency, and future-proofing missions, where kerosene is used because of the high density, simpler storage, lower cost, and proven reliability.